Okay, my friends, one of my favorite subjects, probably be my most favorite, is a dipole electron flood theory, which accounts for all of the material that's in the universe. Now, there is a discussion about how these heavy metals formed and how they were able to create heavy metals, which they don't know how it's done. And I don't either. So I'm going to dig into this with you if you want. If you're a geeky sort of person, you got a little geek in you, you're going to go for this, because I really don't know, to be perfectly honest with you. I am going to show you some salt table experiments. Knock your socks off. Wait till you see this. Because everything is frequency and vibration. Just like Tesla said, everything is vibration. And when they vibrate a certain frequency on this table, salt, which is a polar molecule, has a positive and a negative side to it, like little bar magnets, just like the dipole flood theory particles. They shake at certain resonance and then they lock in. I'll show you too. It's amazing. Okay, my friends, I'm going to give you just a couple of minutes of how elements are formed so you'll understand why they're having so much trouble understanding how the heaviest elements formed. And I think I can explain it. And it is going to be a shocker du jour, I'm telling you. All right, this is from BC Stargazers 10 years ago. Now, this is what they're going to do. They're shaking that platform. Now, what they're going to do is put salt on this table, and then they're going to vibrate it. Salt is a polar molecule. It means it's just like a little bar magnet. It has a positive side and a negative side. They're Na way down over here and Cl way over here. That's just like a bar magnet. So they're going to shake and shake and shake and shake, and then all of a sudden, at a certain exact frequency, they lock in. Watch. All right, before we get started, you have to understand, this is what an actual hydrogen atom looks like, the proton. Hydrogen is supposed to be one big proton like this, and one tiny little electron floating around it. It doesn't work that way. There's 1,823 dipoles together. That's why they stick together. And at a certain frequency, boop, and I believe it's 1823, they lock in pretty solid. Now, as they decay, they fall apart and they shake around like crazy, but then, bam, at a certain frequency, and you'll see this very shortly, boom, they just lock in. And then when it gets more and more vibration in there, they lock in again, and then they lock in again, and they lock in again. When you're in the hydrogen-helium range, you see on the first line here of the periodic table, that can only go up to 4 surrounding fields. Same thing with helium. And helium uses up to all 4 of them. Hydrogen only uses 1. And then you go up into the rule of 8, which there's 8 in the rest of them that surround the core. And you'll see this in that pattern when the salt shakes. See, this is my theory, dipole electron flood theory. A friend of mine, Oscar Rosales, has got a website going here for it. And these are the only 2 particles that exist, a white one and a black one. And this is what a gluon looks like, which is one of these little dipoles. It's just one of these. But it's a magnet. You stick 2 together, it makes a photon. That's what we see as light, is a photon. There's going to be a lot of changes, and the periodic table has to change. So this is not just 1. This is 1,825 or so particles. Helium, you're all the way up to 7,350 or something like that. So I'm going to show you this salt locking in at these different frequencies. Okay, don't forget, this is BC Stargazer. Now, this is the frequency shaking this plate. Boom, you see that? They were all just everywhere, but they're all little magnets, and they will push against each other and pull each other. And then we found that the black can separate from the white, and the black is going into the center, being pushed bang, and at a certain frequency it locks in. Now let's see, 1, 2, 3, 4. That's the 4 orbitals. Now hydrogen uses only 1, but helium uses they say 2 protons and 2 neutrons. Well, it's just helium uses as much as it can surrounding that core. That's the only two that exist in the first row, into this very tight. As you get bigger up here, it goes to the rule of 8. So here it goes. I'm just going to keep going. And as they go bigger and bigger with the hertz, just means numbers, frequencies per second, cycles back and forth, up and down in this case. All right, and in a 3D, this is a whole different story, but you're going to have like a ball in the center, and then you're going to have these orbitals around the outside. This is a 2D flat. All right, so here goes. Now they're going to go up to the next frequency, and you're going to see the rule of 8. Watch. Zip, boom. At 1033. Look at how crisp. Now these zones have to be pushing the dark matter to the center. This is all I can tell you. You still have your lowest orbitals here. And then you got your rule of 8. And then it's going to go up higher and higher. And you're still going to have that 8 looking effect. Watch this one. This is 1820. Now if you look around, you're going to see, you know, there's 1, 2, 3, 4. And the opposite is going to be 5, 6, 7, 8. There's patterns come out. Well, you can see it's patterned. And so everything is vibrating against each other with the polar. Here's 8 again, see? It just keeps going up and getting more and more complicated. There's 8 again in the center. Isn't that amazing? Now, when you're going to get into the heavy metals, you're going to be way up here. You see how complicated that is? In other words, you're going to have every one of these is a salt grain. All right? You're going to have just scads of them all surrounding this one glob. And that's going to be, apparently, I would think it was going to be your heavy metals, because it's just got so much of them. Now, how do they stay like that and they don't just fall apart into smaller pieces? Well, that's a good question. I'm trying to work it out. All right, this is Oxford Academy Analytical Toxicology, and this is about what is in whole blood plasma and so forth. Now, there's 27 metals that they looked for, but there were just literally all the metals are in your blood, and I believe that's where metals came from blood. Look, all these are different metals. Metal, all the way up to uranium. This is in blood. All right, this is a serious study. Now, it was in Canadian, I believe. And these are whole blood. I don't know, the Canadian people are probably similar to us. Anyway, in North America, anyway. So anyway, whole blood. Well, what was in it? They had 106 volunteers. Look at what was in it. Lithium, beryllium, vanadium, chromium, manganese, cobalt, nickel, copper, zinc, arsenic, selenium, rubidium. All of these are metals, all the way up to uranium. And then they go down to plasma, which is not whole blood. And then they had another one on here, which was just serum, which is, I think, mostly lymph. But all of these things, mercury, uranium, I mean, it's in there. So where did that come from? All right, let's just take a quick read on this. So they say the new evidence challenges the origin theory on the universe's heaviest elements, anything above iron. So this just came out today. After its birth in the Big Bang, which they say the universe just happened like this, everything just came from nothing, and it was a Big Bang. Quite obvious, everything from nothing. The universe consisted mainly of hydrogen and a few helium atoms. These are the lightest elements in the periodic table. Yes, helium and hydrogen. Now, more or less all elements heavier than helium were produced in the 13.8 billion years between the Big Bang and the present day. So they say it is 13.8 billion years between everything from nothing and expanding, and it all coming back together and making itself into heavy elements. Now, stars have produced many of these heavier elements through the process of nuclear fusion. Well, I have something to say about that too. However, these can only make elements as heavy as iron. So this is the periodic table. Heavier, heavier, heavier. Iron is right there. Now you got all this stuff up here. Where did all that come from? Right? This is as much as they can figure out. All the rest is just, but I just showed you, I think, all of these things, all the way up to uranium and everything else, is in blood. Well, how did it get into the blood? All right, so it says, however, this only makes elements as heavy as iron. The creation of any heavier elements would consume energy instead of releasing it. So they just have no idea how this happened, and then they come down to the end result here. It says, the findings suggest gamma ray bursts, which is they were pinning it on that, may not be the hoped for crucial source of the universe's heavy elements. Instead, there must be a source or sources still out there. As far as I'm concerned, everything was made and created as life, to be alive. As far as I'm concerned, virtually everything. Everything I've found, finding me something that was never alive, I'd like to see it. A lot of stuff has eroded and now is in mud and clay and all that stuff, yes. And a lot of stuff has transitioned from bones and so forth into stone, yes. But as far as I'm concerned, even the stuff coming through space, and I'm going to show you right now, because they're talking about heavy metals, I'm going to show you where they come from. And how would you get a heavy metal meteorite with blood inside of it? Explain that one to me. Now check this out. This is outrageous. This is a meteorite. And it's cut right like this, and you can see all of these crystallized forms inside that meteorite. And I'll explain to you why that happened. And let's look at them carefully, because most of you, oh yeah, look, it's metal. No, it's more than that. All right, this is that meteorite. It's cut right straight down the middle here, and this is all of the fibers that are inside. And you say, well, what are all these fiber-looking things? Well, there's a couple possibilities, but one thing is for certain. When they are different colors, they are different molecular structure. What does that mean? Well, I'll tell you what it means in a second, but I don't want to shock you yet. All right, so this is a meteorite. Well, what is all these different colors? Well, they're all different metals way up here, because everything burns off. You end up with iron basically and up. You know, you get some of these metals down here, but all of that stuff burns off, the cheap stuff I call it. I end up with chromium and some vanadium, probably titanium and some, whatever. Up this whole area ends up smelting. And then when it cools down, they sort of migrate together and they form these crystal patterns. And the different colors means they're different chemistry. Now, there's also something going on with all of these different fiber-looking things. They look like fibers to me. Now, this is blood right here. You see that? That's blood. That is an artery. All right, and it came right in through that sidewall there. That's an artery. Now, there's always a vein when there's an artery. Boom. That's the vein. So we got a vein and an artery. Artery, vein. Vein is black. That's the used blood. You see? Now, what are these fibers? Are these fibers just different crystals of metals? Could be. Or they could be connective tissues versus, the wet materials inside of a heart or liver or whatever. But this is, I would say this is either a liver or a heart. But a lung will do the same thing. A lung will turn like this, only there'll be a lot of holes in it. I'll show you one gigantic one. But I believe this would probably have been a liver, because liver is almost solid blood, and the heart is also almost solid blood. And I showed you this. That's solid blood. That's just literally solid blood. There's some tissue on there, but that's the cheap stuff. That's the stuff that burns off. You end up with this stuff, and the metals all turn into a blob. And that's why they turn into those crystals. Now, there's going to be some fibers in there, too. There's these strappy fibers. They're tough. They may have survived as well. But this is going to be, all that metal is going to go to a ball of gooey metal. That's what smelting means. And then it's going to end up, whether or not these fibers were left in there and then they just congealed around the fibers, or whether they made their own little crystals. That's to be determined. But I can tell you what is not necessary to determine. That is blood. I would say I would say that there's some of this fiber is the fiber of the fabric of whatever this organ was. You see how some of it's black right there, and there's all this color, and then there all those little. To me, I see a lot of biological features here that are fibrous, tendinous, connective tissue-ish, bloody-ish, metal-ish things. That's what I see. All right, I showed you all the metals that are in the blood, and these are these transition metals. This blue area here. Iron's way down here. All of these are in the blood, all the way up to even uranium, as I showed you. Now, they're showing these are the important ones for biology that mostly they see. And they attach, these are what's called ligands, and they hold molecules of certain types around the metal core, which is one of these, using the charges that it has. You see, they have a positive charge, and that's what attracts these molecules. Then they bring them, and then they just distribute them. And then they go back and get charge up again and take some more stuff. Transition metals form colored compounds and complexes. The colors vary depending on the charge on that metal ion and the number and type of groups of atoms that surround it, called ligands. In watery solutions, the ions form complexes with colors shown to the right. Now, I'm going to show you these colors in a second. The electrons are arranged around the nucleus of the metal atom, you don't have to worry about that. This is what they look like in their colors that represents these different metals. And those metals normally come down and deliver things. But if the thing died in a certain situation, these become opals. They come down, attach, and don't leave. But they find a certain body tissue to attach to, and they attach, and it's spectacular. You see this? I think this is a pacemaker or something, but it has nothing to do with what we're talking about. These are the different types of tissues. You see this darker looking tissue, and then you see these like filaments, and you have walls around it and so forth, and your aorta and all that business. Well, to look at it, they just look like brown tissues. But they have a specific chemistry, and I mean specific. So when that thing died in the Yoa region of Australia, it was soaked with silicates and blood for a very long time, it appears, and it invades. And watch what happens to a heart when this happens to make it opal. All right, don't forget. These are the transition metals. these are the colors. This is a heart. That's a heart too, and it's cut in half. Now let's take a look at it. Don't forget, these are the walls and the different, heart strings and all that. And here it is, cut right in half. Now that side would have been down, and I know that because this side has the red patch here, which the metals are heavier, and these are metals. The plasma would drift up to the top. So this whole thing would have been laying this way. And it's cut and it's open now. This is the top. These are the ventricle walls. They obviously wanted to find whatever this green molecule is to attach to that specific type of tissue. No question about it. And in this area, it didn't have enough of the blue, so it took on some green. There's a lot to look at here, a lot to understand, but preferentially, this wanted the blue. And you see, like I said, this is up here, this is down. So the green is probably heavier, and it went to the lower part. There's a little bit up here, but this would have been higher up. So the red stayed up here, and some green invaded down here. Whatever the green is, it's got to be heavier than the blue, I would say. Specific gravity brought this stuff down. All right, metals are heavier than this. So there's some thinking to do. All right, check this out. This is a lung, and it's just all deteriorated. There's a little hole that goes into all the different alveoli in the lung, and these big cavities have these little tubes running in. Now you see, this is one of these same cavities, just like this, and here's that little tube hole on the bottom, just like that. All right, because this is a lung, only this one burnt off in space, and you want to see what it looks like in its fullness? There it is right there. That was the spot where I was just showing you this right here with a little hole going in, just like that one is. And all the cheap stuff burnt off. Now this was here on Earth, and it just leaked out and kept the fabric. This one, the fabric burnt off and just kept the blood. It's just the opposite. Now I have iron meteorites here. This is one, and this is a lung. That's a lung. There's the latch right there. I can show it in a microscope, shown it a dozen times. This is, it's magnetic. You know, it's turned into metal, which they smelt off. Now all of these holes are the same as that. It didn't burn up as bad as that one, but in a microscope you can see there's still blood in here. If this was cut, you could get raw blood out of there. And by the way, I think you could get raw blood out of that other one. It sure looks like it to me. I think you could get, I'm certain you can. I mean, when it's red like that, it's in pretty good shape. And this here, I could see it, no problem whatsoever. You can get blood out of this. Because this didn't cook up as much as this. So the smaller they are, the less they cook. I have another one here. There's another lung, exactly identical to this one. Identical. You see, it's just smaller. It has the same latch and everything, just like that one. Has all the same features, exactly identical. It's magnetic. All right, there was all kinds of different size creatures. As you saw, that one was just enormously gigantic. This one here is a meteorite, but it's a bone meteorite. Hold on. But still, wherever the blood was, you see it boiled out there? That was where marrow was. The rest was bone. Here, there's no magnetism at all, nothing. You see? But here, where the blood was, it's turned magnetic because it boiled off, and the blood has all the iron in it, just like this. All right, this would be called a stony meteorite. Well, I call them a bony meteorite. And the other one is a lung, iron meteorite. And this little one here also has some magnetism to it. The smaller they are, the less they cook off. So this one doesn't have nearly the magnetic attraction that this here, because that's raw blood. When that cooked, it cooked. And this one here cooked even more, because there's more metal in here. Is it just, anyway, I think that makes it semi-clear. This is in space. I'm telling you, I think everything there was that's metal is from biology. And I think everything in space is biology. They just came back from Comet Bennu, which is a heart. I might as well show you, because it's very hard to believe the things that I claim unless you have open eyes and you're willing to understand what you see. I do the chemistry. I do the biology. I do the atomic stuff all the way down. You have to do everything, and then you have to go back and look at the ancient texts and see what they say. And I understand it all right now, and I'm glad that I was pushed back against, because I was forced to keep going more and more and more into this. And I think I fully understand just about everything about this now. I understand about the electron flood theory, the chemistry, how it works with the biology, how it preserved all of the mud fossils, why opals form versus other things, what's coming through space. Now let me show you Bennu's psyche and what a heart looks like. Okay, here it is. This is the anatomical portion of the heart at the valves. This is all this plumbing is gone. Right about here is broken off, and you can see right down into the valves. Now, they just had a spacecraft come back from Bennu. This is Bennu. You see this? You see this? This is Bennu. That's a heart. That is a heart. And you see that? That's not a crater. That's a tube coming out of that heart. That's a tube. And so is this one. You see these colors? The two separate colors? That's because you have, and there's also the black. You see the black, the red, and so forth. And also you see this. That's tendon. And these are blood colors. And these are the valves, and these are the tubes coming out of the heart. These are tubes, not craters, tubes. Explain that. Now, that is Bennu. Well, guess what? As I showed you before, these hearts are almost 100% metals. There's going to be some body tissue, and this one still has some body tissue. Now, there's another heart. The psyche is virtually identical to this, only it got too close to the flames. And here's what happened to psyche. It got melted. But it didn't get destroyed. It just got melted and not completely cooked off and melted down. But it also had tubes coming out of it. And that's metal. This is metal now. All right, and they know that. That's why they're so interested in, we're going to find a bunch of metal. Yes, you will, because it's primarily iron. But it's all those other metals too, which are blood metals. This is where it came from. They didn't just come out of nowhere. And this Big Bang stuff and evolution, I'm not going with that stuff anymore at all. That's crazy. When you see what really is here, and you see how much pushback against reality there is. And here's the heart right here. Look at this. This is a gigantic heart. I'm not exactly sure where it is, but there's a guy standing over here looking at it. That's heart muscle. And these are the aorta and so forth. Now, I think this is another heart here, or it could be a lung, because you got hearts and lungs, and they both have tubing coming into them. That's the muscle. There's some guy standing there. I believe that's probably a lung. Yeah, you see all the little holes here? I don't know. It's hard to tell. But if you're going to have a heart, you're going to have a lung fairly close by. So now check this out. Here you got Bennu. Well, what's this stuff doing here? If you can see that really carefully, you can see there's little lines coming up here. That is a tendon. This whole thing. And what a tendon does is it anchors muscles. So this reached out to the muscles so that the heart could do that and pump, squish, squish, squish. Now, that's the anchor. Now, I'll show you on a real heart. There's the anchor right there. That's, you know, it turned upside down, obviously, but, or is it obvious? Hold on. Well, whatever. There's your valves, and here's your tendon, locking it in, and the muscle wraps around that way. So just think about it that way. All right, so the tendon locks in here, and the muscle wraps around this way, and that lets you do this. And this is the delineation of the ventricle wall, so you got your separation of your vein and artery blood, and you got your major plumbing up the top. This erodes away. That's why that turned into red and black and orange looking stuff, remember? You see the red and some black and orange looking, and then right next to there is the valves, and this is where the tendon is, reaching out to the muscle. All right, this would have eroded away and left just the valves, because that would have gone too. All right, remember what you're looking at. What we got here is reaching out over the top to the muscle. This stuff here is gone, and this is all gooey. But you're going to see the valves here and here, which is exactly what you got. There's your two valves, and all the other gooey stuff is gone, and the tubes are gone too. They sort of locked in right around this area, but they rip off right there, and you end up with these valves just sticking out. And of course your tubes, and the different colors are the separation of the blood. The black is your vein blood, the red is your artery blood, and the yellow is like a plasma-ish blood. Lymph, more or less. And this one, like I say, this one got smelted to a degree. It must have got to come really close and then just kept going somehow. Escaped the pull and just kept going. That's Psyche, it's called. This one's Bennu. They took a sample off of here and they brought it back to Earth. I know exactly what's going to be in it. I just showed you what's going to be in it is all that blood chemistry. All right, so I think this is pretty clear. All right, this is the National Library of Medicine. I don't think they understand the transition metals. They're talking about trace elements and metals in the body and pretty much showing them as being toxic and lead and all this bad stuff for your body. Now, they do say some of them appear to be necessary, but I don't think they understand how they work, and they certainly don't understand this one. They got vanadium. All right, vanadium is a trace element that exists in multiple oxidation states in the body and forms complexes with proteins. Proteins are the things that you absorb and you eat and build your body. Vanadium has not been shown to be an essential element. Now listen to this. And indeed is poorly absorbed. You don't have to absorb it. It's just supposed to float around in your bloodstream. You don't absorb these things. They're used to carry things throughout the body. They're transition metals. All right, so anyway, I don't think they understand how these trace metals actually work. Here's tin. Let's see, as a trace element metal is widely found in nature, detectable in many tissues and nutrients. Tin deficiency has been described in rats, but has not been clearly shown to exist in humans. Its role in normal human metabolism is not clear. They don't understand. It's used to carry things throughout the body. That's what these transition metals are all about. just to be clear, tin is not actually a transition metal. Tin is SN for some reason. All right, so tin is over here. It's in the other metals. It's not a transition metal, but it basically does the same thing. But it's more towards this other end where stability comes in to play, I believe, in the metalloids, or maybe even instability. I don't know, but it's another metal that they have to understand, and they don't understand how these metals transfer things through the body. And this is a heart. Those are hearts. I don't care what anybody says. These are hearts. All of these. Boom, 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 boom. That one's obvious. Boom. That's a good picture. This is where all that plumbing breaks off right there. Prip, and there's your valves. And there's the little tubes we saw sticking out here and there. You see? These are the valves we're seeing. Well, that plumbing just breaks right off. I had a guy find a heart, a Mudfossil heart, and he just tapped it right on the side like that, and all that broke right off, and inside was raw red blood. I'm not kidding you. It was, he put his finger in it. It was all red blood. So I guess I showed you that. You see that? That's the top of the heart. That's the big red blood chamber. And then this is the rest of the plumbing coming out of here. You see how much plumbing coming out of here? All of these different tubes coming out of here. And that's what was coming out of the one Phil found. This was Phil Harris, a good friend of mine. Unfortunately, Phil passed away. But he took the challenge to go out and find it. He found this rock, and he hit it where there was a red blood spot right here. I'll show you in a second. And he hit it with a hammer, and it broke right straight across like that. And these were where the valves were. Now, here's the other side of it. This is solid blood. His fingers are red blood. He saw that spot, and he whacked it with a hammer, and it just opened right up. And one side was sort of dried out-ish, and this side where the blood was leaking out was still wet here. So this side was down. The other side was up. You follow me? If you took this and put it right on top of that, that's how he found it. And he whacked it right there, and that popped off the top. So they the rest is obviously a rock. All right, but you see that? That's the casing of the heart. And the blood stays. I have ones that have blood coming out of them still today. You can't hardly get a rock without getting blood out of it. Well, whoever came up with you can't get blood out of a rock was not correct. This is the crazy part of the whole thing. I come with all kinds of evidence, and they defer to this kind of stuff. According to the Big Bang Theory, matter in the universe originated from a singularity. There was nothing. Extremely dense point. How do they know that? Exploded with great force about 13 billion years ago. The leading model for how this happened is the inflationary universe model, which means all the light is being pulled away. That's the redshift. No, the light is slowing down. That's the redshift. They say, no, Einstein says it can't slow down. Einstein was wrong. All right, so it's an inflationary universe. Everything's going out. So that means we're the center of the universe? I don't think so. It suggests that space was filled with an unstable form of energy. How do they know that? Just before the Big Bang. At some point, this energy transformed into fundamental particles that created all the matter in the universe, and then somehow slime started to grow here and there and turned into artificial intelligence. This is literally insanity. And they talk about my stuff having evidence and supporting CAT scans, DNA specimens of giants, huge, just gigantic giants. I'm sorry, it's just true. And for them not to be able to accept my evidence and to take this kind of nonsense and tout it, and that's why we can't look at your stuff because it doesn't fit this, that's just not right. You know that I'm saying we need a completely new atomic model, which is that space is filled with magnetic particles, because that's what light is. In addition to that, there's all kinds of other debris in space that also has fields. Now, there's something very interesting. This is Rod Warren's nephew, Dylan Carpenter, sent me several pictures, and that was it. I never heard another word from him, and I can't get in touch with him. But these are dipoles. Dipole means your positive and negative attached together, like little bar magnets. Now, what it is, I don't know. It appears to me that it could very well be Venus. I'll tell you why in a second. This, I'm certain, is the moon, which has no field. All the planets, and apparently these are stars or something. I don't know. I got a couple other ones. Hold on a second. Now, he's down in New Zealand, and all I can tell you is he sent this. Now, there's something behind the moon, and I believe this is the moon, that is extremely polar, and it's generating this huge field. It's overlaying the moon, but that's not the moon's field. It has nothing to do with the moon. The moon has no field. And I believe it's because it's not spinning. The moon is just sort of drifting around, but it's not spinning. All the planets spin. And Venus spins backwards. And I'm going to show you why I think it was Venus in that last picture, because it has two fields. I'll show you in a second. But these are dipoles. All of these white and black particles are dipoles. And there's more, they have to be stars, I would imagine. Now, all of these are radiation fields. And what is a radiation field? It's something, it has to be bump, 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 bump. So it's, here is going, and then all of a sudden it just stops at the end. But there's going to be some measurements between this and this and this and that and that and that, and as they're getting just longer and longer and longer frequency as they go out until they no longer can escape whatever they're trying to escape from. But there's fields, and the fields are trying to pull these particles back, and those particles are trying to escape, and they're banging into each other with a vibrating frequency. That's what I can see, and you can see it too. Now, what all the rest of this stuff is, I have no idea, none whatsoever. But I'm telling you, the blue, it appears to me the moon is going in this direction, crushing the light instead of having light expand. It's crushing it towards the blue and expanding a little bit here. So it's going more towards the orange here. That's all I can tell you. Whatever the rest of the stuff is, je ne sais pas. Now look at this one really careful. Very strong dipole. And then you have the field surrounding it, which you expect. That's a very nice field. Then what is this? It's coming straight up the same axis and straight out and around, but it's less intense. This is pretty intense. And this is less intense. Well, why? And why would it be following right up the same axis? I believe this is Venus, and instead of Venus spinning the normal way, it's spinning backwards and going forwards. So everybody else is spinning in a certain direction, almost like it's rolling around and rolling against what it's coming into contact with. So it would be rolling like this, around and around and around and around. Venus is going backwards, but still coming this way. So it's scrubbing, creating one field, and spinning this way, creating the other field. That's all I can take from that. That's too much for me to deal with, other than that. That's the only way I can account for that. That's the only way you can account for that. And also, you see that's very unusual too. That should be very black and very white. And you see it's almost black and white. And then black again, and splayed out black. Normally the black stays pretty tight, and the white is the one that splays out. I'm almost sure that's Venus. If I had to bet, that's what I would bet, Venus. Don't forget, this is what they say during the Big Bang, which I don't believe in anymore. The universe consisted mainly of hydrogen and a few helium atoms, and then everything got big after that. Well, now they realize that just doesn't work. These findings suggest gamma ray bursts may not be the hope for crucial source of the universe's heavy elements. Instead, there must be a source or sources still out there. Yes. Now, what they are, I'm not sure. We're going to look into it together and see if we can figure it out. But I'm going to tell you right now, this is what an atom is made out of. All dipoles. But the dark core can go right to the center. That's why they've never seen dark matter. It's in the center of everything we're looking at right now. That's what gives everything weight. It's just like it's right inside here. See? There's your dark matter right there. And all of these are the white particles. And we can separate those from the black. We've done it with the light experiments. Now, when they come back together, and right now we've seen them come back together and just reform as light. Is there a way in some crushing device you could force them to come back together as heavy particles? I'm not sure. But we can show you, or I can show you them. All right, the Big Bang makes no sense whatsoever. That would mean that we are the center of the universe because everything is moving away from us like we were the beginning of the Big Bang. And they say it's pulling the light away so fast that by the time it hits us, it's shifted to the red. No, it's not. It's just by the time it hits us, it's just slowed down. Because these things are just out there. They didn't come from a Big Bang. From nothing, came into everything. I think I'll just leave it at that because I've shown all these particles. I could show they speed up, they slow down, they are particles, they have a mass, the black part, the white part has no mass, has all the burn. It solves the situation we're in with the atomic model. This is it right here. This is the new atomic model. It's dipole electron flood theory. And the dark part of the dipoles goes to the center of atoms. We show it actually separated. These particles can actually separate, and we did separate them into their separate parts. They're normally glued on like that together as an electron. Two of them back to back make a photon. Photons bounce off things and you see them as light. This goes into things as heat or electricity, lightning, static, and so forth. This bounces back because it's a photon. It's a complete magnetic field. And it changes a lot of things. And one of the things, the redshift is just ridiculous. It doesn't shift because it's being pulled away and everything's just expanding so fast. It's being sent from there, and it's just slowing down as it comes towards us. That's all. It's got to interact with every kind of field that's in front of it, and there is a zillion fields in front of it. Every time it interacts, it slows the fields down a little bit. All right, my friends. The physicists claim that everything is expanding because of this Big Bang and stretching the light, so we have a red shift. Every single astrological and astronomical distance is measured at the speed of light, never changing. That is just completely insane. Speed of light changes very fast, and light has to move through fields. When they move through the fields quickly slow that light. We really have absolutely no idea where we are in the universe right now because we think the speed of light is consistent. It's not. You see this? These pictures were taken by Dylan Carpenter in New Zealand, and he had a new phone with some kind of app on there that gave these field effects to these dipoles that are in space, which all planets have a field around them, and he was able to capture this. And all these stars and whatever they are, moons, I imagine they're stars, but they all have their own fields, and those fields interact with other fields. And as light passes through these fields, it has to bang through them as it goes. And as it does that, it could be coming in really hot like this. Boom, 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 keeps stretching out as it hits these. Depending upon the density of the space that the light is traveling through and how many fields it has to pass through, it could slow down to almost zero, and I say pretty quickly. And that's what the cosmic ray microwave background is. It's so slow, it's just light that's almost just not moving anymore. There's no mystery here. It's just light that it was going fast and it keeps slowing down, slowing down, slowing down. So everywhere we look, there is no speed of light that's consistent. And that is no question whatsoever. I show you right now. It's absolutely certain. All right, you've got light coming in from a pulsed red laser, and it's bouncing into all these fields, like I told you. It's going to slow it down. In this case, it's speeded up because we have a Venturi here. Normally, it would slow down. The blue one, I'll show you in a minute, slowing down. The particle itself is being pulled out of the wave because of the Venturi. And at the Venturi, it explodes and divides the black from the white. Normally, the black and the white are attached just like this. That's a photon. Half of that is a gluon. The black is a muon, and the white is an electron neutrino. And this is the red. They come in blue and green. And this is just starting to accelerate. This is very fast acceleration. This is coming through the Venturi towards us, and it creates the Higgs fields. And this is just a totally unknown. I believe that's a backward spinning particle that is the strangest one I've ever seen, and I've seen thousands and thousands and thousands of these. Okay, these are the particles that Fermilab and CERN find. The smallest ones they can find is this one is a black one, never changes size, has a glowy edge, and this one is the puffy one, gets big and small and has no mass to it. And they say that empty space is not empty. Now this is Fermilab. This is quite a while ago, over 10 years ago. Empty space isn't empty. It's full of these subatomic particles winking in and out of existence. They have a measurable impact on our universe. Yes, it slows the light down. When they wink in and out of it, means light is hitting them and slowing down and down and down and down. That's as simple as that. So don't forget, these are for the giant colliders, but they're hitting huge particles. And instead of smashing, like here's what they're doing. They're taking protons and neutrons and smashing them together and getting just enormous piles of debris. What we did was we took light. So the actual one of these protons was nothing more than 1,823 particles. We were down here, so we didn't have to have all this debris, and we could actually see the particles. These are the particles they're seeing. It's the exact same ones we were seeing. But don't forget, we started with light, which is the smallest particle that exists. This was the Fermilab. See, Fermilab point particles. Here they are right here. This is what we found. That's a photon going this way. This is photographed with CMOS, which is complementary metal oxide semiconductor silicates. And, excuse me, you can see absolutely fabulously with CMOS. And CERN upgraded to be able to use CMOS. All right, so let's just follow this through. These are the Fermilab point particles. The glowy edge never changes size. It's called fixed. This one has really no mass, but all of burn. Exactly what we found. These are the black ones. They have the glowy edge. These can get big or get small. It depends on whether they're getting excited or not. This one's being excited by moving through the air in this direction, pushing against these fields. Now this one's depleting. Now it'll eventually, this one will get so excited, it'll flip, and this one will come forward and pump up and it'll flip. That's called a muon wobble. Now, can we divide those two particles? Yes, we can. What's that called? Fission. Can I show that? Yes. What would this be called? It would be called a muon, sterile muon, all by itself. And this would be called an electron shower because it will go into a shower mode. Here is the actual physical evidence to support that. The light speed is accelerating because of the venturi. A venturi forces things to accelerate, just like the nozzle on a hose. The water coming in the hose is coming in at 1 mile an hour. It comes out of the hose 20 miles an hour. It's a venturi. They used to have them in carburetors for cars, and they would sip the gas into this airstream, and it would make it turn into a shower of particles. It would be called atomization, and that's exactly what we're doing here. But it has to accelerate to atomize. We're atomizing atoms. So we're subatomizing. This is a subatomizer. It just came to me. So here it comes. Here's the particles. Pow! And what happens? The black stays this side, and the white goes through the venturi. That's fission. And back together is fusion. There's no other way to look at it. And this is the shower. You see, electron shower? These two are together, the black and the white. Right? You saw that. I know you saw that. There they are right there. And they were stuck together. And they're stuck tight. They're tight. They will not come apart until you hit them with the super collider or do what we did through the venturi. And at the venturi, only the white can get through because it can squish down. The black can't. These are the same size balls. Every one of them is the same. Some of them don't look the same size, but that's only because they're engulfed with whiteness. But this is what it boils down to. The muon goes on its way as a sterile muon. The electron turns into a shower, electron neutrino. This is precisely what happened here. There's no confusion here, none whatsoever. Okay, I guess I'm going to have to leave it with this, but as I've been showing for a long time now, that laser through that venturi separates the black part, which has no energy, has all the mass, from the white part, which has all the energy and no mass. This is what you want to put into a car, or any electrical circuit, battery, whatever. Only the white, not the black. But to separate them, normally it takes a hell of a, literally tons of amounts of energy to pull them apart. So that's why to generate electricity, it takes more energy to generate it than you get back, basically, or that type of thing. This, we didn't do anything whatsoever. All it had to do was pinch it tightly enough to only let the white through. So what does that mean? We could put this in something like this and just carry it around and plug anything you want into it, have any power you want coming out of that little tiny box, and have literally thousands of these within that enclosure. You're not on any grid, you're on nothing. You just dial in whatever you want, whatever is voltage, AC, DC, USB, whatever. I think that's doable. But somebody's got to look into it. I can't do it. But you need a solar collector type thing right here, through a photodiode down into a circuit. This is quite simplified, but it's very, all you're going to do is push electricity in just like a charger. That's all. And it'll go down in there. Now, you should have an excess, and just take a little bit of it and keep the laser going and just keep building more and more and more into the battery. It's charging it up. And the more of these you had, the quicker you would charge it up. And the higher the frequency and voltage and so forth of the neutrinos, which is, you want to be way up into the blue range. They're real powerful, I would think. There's some work to do. But using they have what they call perovskite, thin film, solar panels now. They're working on it. I don't think they actually have them perfected yet, at any rate. But they will absorb all this extreme different frequencies of light. It's just off the scale energetic. If you can capture that energy before it gets back to the black, which it will, it reattaches to the black right there. If you can get it before attached to there, it will want to get back to that black, and it will go through any kind of motors, and it'll burn right through you. All this is lightning in a bottle. That's all it is. This is exactly what lightning is. It's exactly what static electricity is. It's exactly what nuclear, the first wave of nuclear particles is. They just burn things up and they have no mass. That's what this is. That is raw energy. That's a lot of power, even with a little laser. So if you had a batch of them in here, you should be able to create tons of it. And it immediately comes back to the black if you didn't intercept it. If you intercept it, then you store it. But you're only talking with a very short distance. So inside that enclosure, I don't think there's any danger of getting irradiated or anything like that. We're working with light particles. These are the tiniest particles there are. But that's what they want to get to when they do these nuclear explosions with these colliders. They smash them together and they want to see these particles. That's what they're looking for. That's exactly what they're looking for. But we started with light, and what we did was we sent them through a Venturi, which is a very tight restriction. And when they went into the Venturi, the white was able to squeeze through and the black could not. So that's the separation. And when you run a motor, what you're doing is forcing extra electrons out the wires as it comes around and pushes and pushes and pushes and pushes. But you have to push. This is doing it all by itself. That's why you need a motor to run a generator. And as it comes, it goes boom, 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 boom. I know this. When I was in the Army, I was in precise power generation for nuclear missiles, so I understand this quite well. That you had to have no bumps in the power. Anyway, this is. I don't see this as being a big deal. I really, honestly don't. And anyway, I'm going to leave it at that. All right, I love you all. They just don't understand what the universe is made of, first of all, and any physics or basically anything. Let's just boil it down to the true nature of everything. Chemistry's wrong because they don't understand dipole molecules. I'm not going to go through them all, but to think of something that is right. Think of something that is actually right, and then let's discuss that. All right, I love you all. Bye.